Today, we're going to discuss Bernoulli's equation, and we're going to build up to Bernoulli's principle, which you guys have probably heard of before. It's how a wing provides lift for an airplane. It's also how sails work for a sailboat. So we're going to build up from the things we've talked about in the past to this Bernoulli's equation, which is kind of like the master equation for fluid dynamics at the level that we are discussing. So let's first think about the conservation of mass and energy. All matter, all things in the universe have to obey the law of conservation of mass and energy, and fluids are no different. So we talked about actually last time the conservation of matter. I didn't name check it as such, but that's what defines that continuity equation, right? And that tells us that the same volume of fluid moving by one point in a closed vessel will be the exact same volume moving by any other point over the same time period. We're going to add on top of that, we're going to consider the conservation of energy today, and that's going to get us to what we'll call Bernoulli's equation. So let's first consider the total work being done on a fluid. Remember that because fluids don't have a rigid shape, when we push on them, unlike with a rigid object in space, it'll accelerate in an obvious manner. If we push on a fluid, it's going to move around our force, right? But if we have it in a sealed container, then pressure is going to be how force is communicated to and by a fluid. As fluids pass through their vessel, they feel a positive force/pressure from one direction, and that's what we call the upstream direction, and a negative force/pressure pushing against their flow, or negative pressure coming from downstream of their flow. So the upstream pressure will be greater than the downstream pressure because it has to be, because if we switch those, then our upstream and downstream also get switched, right? So basically what we've got is over here on the left side, this is our upstream, because that's our upstream, and our force is being applied in the direction of our flow, right? So again, basically that force is pushing the fluid along to go through what we call a stream until it gets to the downstream. And there's going to be some pressure on the outside in the environment at the end of this vessel as well. And that pressure is going to be pushing back in the opposite direction that it came from, right? So there's that negative pressure down the downstream and a positive pressure over to the upstream. The difference in pressure, that difference in pressure will provide a net force, which does some amount of work on the fluid as it moves through the vessel. So we can set up our work equation. We know that our net work is the sum of all the works being done on the object or the system that we're looking at. So since we have some work being done over here at point one on the upstream end of our fluid, and some work being done on our objects by the force at the downstream end of our fluid, then we can take and we can make a net work equation for those two forces and the pressures that are providing them. So obviously we know that for work, we can break down work into force times distance times the cosine of the angle between the force and the direction of that distance or motion of the object or the system. And so if we look at point one over here, upstream, right, we have some force that's being applied. Call this F1, which is F1 right there. We have some force F1 pushing that direction, right? In which directions our motion is the motion of our fluid particles going? They're going in this direction. So right here is D1, right? There's some distance they're moving based on that force that's being applied over at point one. And of course, there's some angle between the distance and the force, and that angle there should be 0 degrees, right? So our angle over at point one equals 0 degrees. And then if we look over at our second position, downstream here, our force is pushing back against the flow. So there's force 2 as our particles move in the direction towards that force, or I call that D2, the distance that they move while they're pushing against that force over the time interval that we're looking at, right? And so we can find a work expression for that. It would be F2 times D2, And we again want to take a look at the angle between those two, the force and the distance, both those vectors. And that angle right there is an angle over at position 2 of 180 degrees, right? And so if we plug those numbers in, we know that cosine of 0 is 1 and cosine of 180 is -1. And so we can substitute in those terms. And so we can substitute in those numbers, 1 and -1, and we end up with this term now that F1d1, or the force times the distance that the particles move over some time interval over at point 1 over there on the upstream portion of our fluid, minus the F2 times d2, or the force felt at the downstream portion of our fluid times the distance they're moving over that same time interval. And that should equal our net work, right? And then we could break this down. We know that our force equals pressure times area at both F1 and at F2. So we can substitute those into our equation there. So our net work equals P1 A1 D1 minus P2 A2 D2. And finally, we know that area times distance is the volume of the fluid moving by that point over that time interval, right? So P1, or pressure at point 1, times the volume at point 1, minus the pressure at point 2 times the volume at point 2. That will equal our net work. And finally, we can pull out the volume. We end up with P1 minus P2 times volume equals our net work. And we're going to bank that. And then we're going to think about another way to look at work, because we know that the total work done on the system causes a change in energy to that system. So since our net work equals a change in energy, we can break down that change in energy into the two types of energy that we're going to see exhibited by this fluid, right? Kinetic energy, or the motion of the particles within the fluid, and gravitational potential energy, or the gravitational potential energy felt by the particles at the two different heights that the fluid might be at during its journey through this vessel. And for kinetic energy, obviously, change in kinetic energy equals our final kinetic energy minus our initial kinetic energy, which we can break down into our constituent variables there. 1/2 mass times velocity squared is our kinetic energy. So we take the final minus the initial, we still get our change in kinetic energy. And then finally, we've got our mass there, and we know that mass equals our density times our volume. So we can substitute density times volume in for our masses on both sides of that equation. And again, since we know that our volume and our mass that's moving through our point 1 over here should be the same as the volume and the mass moving through point 2. That's why we now, for our kinetic energy, can set up this equation right here. And for gravitational potential energy, we can do the same thing. Take our final gravitational potential energy, subtract our initial gravitational potential energy, and we know that we have a term mgy, or mgh, mass times gravity times the height at that point. And we could subtract our final minus our initial. And finally, we can do the same thing for that we did with kinetic energy by substituting in density times volume for mass. And so if we look at that, our master equation up here, we've got our net work equals our change in kinetic energy plus our change in gravitational potential energy. And we now have three different equations to plug in for those three terms. So if we plug those in, we get something that looks like this. So our net work, which equals P1 minus P2, all times volume, that'll equal our final kinetic energy minus our initial, plus our final gravitational potential energy minus our initial gravitational potential energy, and substitute in with all those for our constituent variables. And so we can notice that volume is present in each and every terms of this equation. And so we can divide by volume, and we end up with something that looks like this. And our last step here is we've got a bunch of negative terms, and we can just add those. And when we add those, we end up with a very nice equation that has all of our terms for point 1, or the upstream portion of our fluid, equal to all the terms at point 2, or the downstream conditions of our fluid. So what this tells us, right? This is Bernoulli's equation. And this states that for an incompressible fluid in the absence of friction, aka an ideal fluid, the following sum stays constant throughout its flow. The sum of the pressure being exhibited on the and by the fluid plus 1 over 2 times its density times velocity squared plus its density times g times the height that portion of fluid is at. And all of that will stay constant throughout the fluid's motion as it moves through an enclosed vessel under those conditions of an ideal fluid. So we're going to bank that up on the top there. This is a form of the principle of conservation of energy, because if we take note, we'll see that each term actually represents either work or energy, kinetic or potential, in a form that is reformulated to be expressed in terms of joules per unit time. So for instance, if we take a look at the 1/2 rho v1 squared or v squared term, we know that rho or density is mass over volume. So we can just substitute mass over volume in there, and we'll keep mass in the numerator and volume in the denominator. And we'll find that obviously 1/2 mv squared is kinetic energy. So we're taking our kinetic energy divided by our volume, which we would express our kinetic energy in joules and our volume in meters cubed. So all of these terms we could do the same thing for, and we'll find that each of them are in joules per unit volume because, again, remembering how we made them, each term just came from either the work, which is in joules, or the kinetic energy expressed in joules, or the gravitational potential energy expressed in joules. But all of them we divided by volume when we simplified this equation. And so in the end, they are all in joules per unit volume, or often in joules per meters cubed. And this is just a convenient reformulation of the conservation of energy for an incompressible fluid in the absence of friction, right? So again, just a fluid that is behaving like a quote unquote ideal fluid. It should follow this equation. And this is essentially the conservation of energy for that type of a fluid. So let's take a brief look at how this would work for a static fluid or a fluid that isn't moving. And if we take Bernoulli's equation, we know that the fluid's at rest, so all of our velocities will be zero, so those will go away, and we can rewrite it like this. P1 plus rho g y1 equals P2 plus rho g y2. And if we put all those height terms over on the right side, we'll have this term right here, which is really just y2 minus y1 times the density times g. And y2 minus y1 is just the total height of that fluid. And so what we end up back with is that equation for absolute pressure that we defined a few classes ago. Or our pressure equals P naught, the outside pressure, plus rho gh. So you see that actually all the equations we've talked about so far are built from Bernoulli's equation. This is kind of the master equation for this unit. So this has some other applications. So for instance, when the depth or the height of the fluid is constant, then our y1 equals y2. So we could just cancel both those out, and we end up with P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. And this is what we call Bernoulli's principle. And what it says is that as the speed of a moving fluid increases, the pressure will actually decrease. Because if we take a look, if whatever this side of the equation is constant, then if we increase our velocity, we increase this term. And if this whole side has to stay the same, I mean, our pressure over here has to decrease. And so how does this relate to the picture over the right? You might want to take a moment and think about that. But if you come back with us, how it relates to the picture on the right is that actually the narrow space between the tractor trailer and the car speeds up the air particles between them because those air particles are getting pushed together, and so they have to move faster. And that creates a lower pressure pushing the two vehicles together. We're going to demonstrate a little bit of something like this in class, but this is why it's always good to be careful when you're driving next to a tractor trailer or some other large vehicle, because there will be a negative pressure or an inward pressure towards the other vehicle if you guys are close enough to restrict the movement of air between the two vehicles. And you may already see how this applies to sails and airfoils, but basically, an airfoil is the shape of a wing, right? It has this like teardrop like shape. And when the wing is angled correctly, it's going to push the incoming air up and over and push things together so that the air is moving faster on top than it is at the bottom, which has more of a straight path to go. And that faster moving air, slower on the bottom, faster on the top. If we increase the velocity, then that means that our pressure has to decrease on the top and our pressure is larger on the bottom. So in net, there's an upward pressure. And that net force upward is what we call the force of lift. And that's what allows a plane or a bird or a bat or anything with a wing shape to stay in the air as it moves through the air. And as the particles of air move around it, those particles being faster on top and slower on the bottom. And the exact same thing happens with a sailboat. And that's why sails are angled not flat against the wind to catch it, but actually in a way that is along with the wind to create this difference in pressure again that pushes the boat towards the greater pressure and away from the less good the less strong pressure. So there's difference in pressure caused by the different speeds at which the air particles must move around the sail or the airfoil, and that difference in pressure provides lift for the wing or the plane or the bird, and provides thrust for the boat. So last lesson we walked through a problem with a garden hose, and we had a hose that looks something like this, right? And then at the end there is a nozzle, and that nozzle has a decreased area, right? So I'm going to call the area of the nozzle A2. We'll call the area of the hose A1, and we're going to have some velocity V1 as the water's moving through the hose, and then it's going to come out at some higher velocity V2. And we said that V1 is 1.96 meters per second, and V2 is 25.5 meters per second. All right, so first question, what would the pressure be at the nozzle? Remember the nozzle right here, there's going to be some inward pressure, right, going upstream from the downstream or the outside of the outside environment relative to the water in the hose. And so we could call that P2. And that P2, or that P at the nozzle, is going to be the ambient or the environmental pressure, which probably is our atmospheric pressure, right? So PATM. And as we know, that's 101 kilopascals or 101,000 pascals. So once we've established that, we now have the tools to figure out what the pressure inside the hoe is, or the pressure on the internal, the input going into the hose, right? So whatever pressure we're applying to the water, pushing it through the hose. So we can safely say that the hose is pretty much at the same height as the nozzle, so we can get rid of our potential energy terms, and we can just focus on our pressure and our kinetic energy terms. So we know that P1, or the pressure within the hose, plus the speed of the water within the hose times the density times 1/2 is going to equal pressure 2, or PATM, which we already found, plus 1/2 times the density times the velocity over the nozzle squared. So we can take, and to get the pressure inside the hose by itself, we'll take P2, or the atmospheric pressure, and then we'll add to that the kinetic energy term for the velocity within the hose, or 1/2 PV2 squared, or sorry, 1/2 rho V2 squared, and then we'll subtract out the kinetic energy for the water within the hose, or 1/2 rho V1 squared. So we can take, and I'm just going to rewrite this a little bit so that we have P1 equals P2 plus 1/2 rho times V2 squared minus V1 squared. And then we can substitute in numbers. So for P2, we've got our external pressure, right, was 101,000 pascals. And then for our density, the density of water is 1,000 kilograms per meters cubed. And our initial velocity is 1.96 meters per second. And our final velocity is 25.5 meters per second. We want to square those, subtract them, times 1,000 times 1/2 plus 101,000. And so in the end, our pressure at the hose should be about 424,000 pascals, which of course is larger than the pressure in at the nozzle, right? Which means that if we draw that hose again, that there's a larger pressure over here, P1, is larger than the pressure pushing back on the outside at the nozzle, which makes sense because this pressure should be larger so that ultimately the water is getting pushed through and then out of the hose. Let's step things up a little bit with our next problem. So let's consider some fire hoses. Fire hoses obviously are used in major structure fires, and they have standardized internal diameters and extra and nozzle diameters. So the internal diameter is 6.40 centimeters. So if we want to find our internal area, and I'm going to call that A1, right? So we have a fire hose that goes up some height and then sprays out at some height, right? And that change in height is 10 meters. So we're going to go up 10 meters. So our delta Y is 10 meters. And then we've got an area of the nozzle and we've got an area of the hose itself. One, and then obviously we're going to have some velocity over at the opening of the hose, inside the hose, and then some velocity over at the outside at the nozzle, right? And that velocity we can determine with our volume flow rate. And we will do that in just 1 second. But let's first find our areas. So A1, right, is going to be pi times half the diameter squared. And so if our diameter inside the hose is 6.4 centimeters, that's going to give us an area of 3.217 times 10 to the negative third meters squared. And then the area at the nozzle is going to equal pi times the diameter over at the second point squared. And that'll give us, since at the nozzle has a diameter of 3 centimeters, and that will give us an area at the nozzle of 7.069 times 10 to the negative fourth meters squared. Okay, so we got to figure out a couple of things. So the first thing we want to figure out is what's the velocity of the water particles in the hose, and we know that the volume over time or the flow rate is 40.0 liters per second. But to get this into our standard units, we've got to convert from liters per second to cubic meters per second. So we know that there's 1,000 liters for every 1 cubic meter. And if you've forgotten that that's a conversion, you can go through and you can try to convert from liters to meters cubed. And you'll find there is 1,000 liters per every meter cubed. So we're going to and that means that we've got 0.04 meters cubed per second is our flow rate, right? And we know that that equals our velocity of the particles of water moving through the hose times the area of the hose. And so if we wanted to find the velocity of the water particles in the hose, we take V1 will equal our volume flow rate, V over T, divided by the area within the hose. And since our volume flow rate is 0.04 meters cubed per second, and our area we found to be 3.217 times 10 to the negative third meters cubed, and that gives us a velocity of about 12.4 meters per second. And that's the velocity of the water particles in the hose. Okay, so doing a quick reset for the second part of this problem, we again know what our velocity or V1 within the hose is, right? Let's now figure out our V2, the velocity of the water as it comes through and out of the nozzle. So we know from our continuity equation that A1V1 for any point with the area times the velocity of the particles at any point within this enclosed vessel should equal A2, the area of any other portion, times V2, the particles, the water particles speed at that other point, right? So if we want to find the nozzle's velocity, we'll take V2 equals the ratio of the hose to the nozzle, A1 over A2, times the speed at the hose, right? So we can plug in our numbers over there. For A1, we've got 3.217 times 10 to the negative third meters squared, divided by 7.069 times 10 to the negative fourth meters squared, times 10.4 meters per second, or the velocity in the hose. And once we run those numbers, our velocity within the nozzle should be 56.6 meters per second. Okay, so now let's find the initial gauge pressure at the base of the hose. So really, we want to find the pressure at the base of the hose, which is P1, and we want to find the difference between that and the external pressure. So really what we're looking for is we want to find what P1 minus P2 is, or otherwise our delta P, and that should all equal our P gauge pressure. So if we take our equation from up here, we can use this. And let's first think about if any of these terms go away, right? So we know that we're going to increase our height by 10 meters. Let's assume that we're at a height of 0 down at the bottom. So we could just get rid of this term, right? And then if we want to solve for P1 minus P2, we will subtract P2 from each side. So we'll end up with P1 minus P2, but we also want to subtract this term, our kinetic energy over volume for within the hose from that side, and we'll end up with something that looks like this. P1 minus P2 equals 1/2 rho V2 squared plus rho GY2, right, our height, minus that kinetic energy term that we subtracted from the left side, 1/2 rho V1 squared. Or if you wanted to simplify this a little bit, we could take the 1/2 rho out of those velocity squared terms, V2 squared minus V1 squared, and we will still want to add in there rho GY2. And that will again find us the difference in pressure, or otherwise known as our gauge pressure, since that's the pressure of the water inside the hose without the external, subtracting out the external pressure, or P2. So we take 1/2 times the density, or 1,000 kilograms per meters cubed, times our velocity 2 squared, which is 56.6 meters per second, square that, and then our V1 squared, which is 12.4 meters per second, the velocity inside the hose, and square that, plus 1,000, our density, again, times G, 9.81 meters per second squared, the acceleration due to gravity, and finally times the height that we gain from going from inside the hose to the top of the hose, the nozzle, which has ascended 10 meters up to that second floor or wherever the firemen are putting out the fire. And then if we plug all those numbers in, then we get a difference in pressure, or a gauge pressure of 1,623,000, or sorry, 1,623,000 pascals, or 1.623 megapascals. Nice. And finally, last part of this question here is, what is the absolute pressure at the base of the hose? Which, now that we know our gauge pressure, you know what to do with the absolute pressure, which is you add back in that external pressure, that atmospheric pressure that we had on the outside, and we add that in, we get our pressure outside the hose, or sorry, pressure inside the hose. The absolute pressure is 1.72 megapascals. All right. So this is how we use sorry. So this is how we use Bernoulli's equation right here. Is we have multiple terms within here, and as long as we know what values we've got for our change in height, our change in velocity, and our change and our pressures, we can figure out any of those missing values as long as we have enough information. Cool. And we also found out a few things from this problem, even without, we didn't start off with any of our velocities, right? So as long as we knew our flow rate and those difference in areas, we were able to calculate our velocities without knowing them immediately. So this equation and everything we've built up here for our fluids is very useful because with a pretty limited set of information, we could figure out a lot and predict many things about the behavior of a fluid as it flows through an enclosed vessel. Okay, so let's take a look at one last thing here. So Torricelli's theorem is super useful when we're thinking about water flowing out of a large store of water through a small hole somewhere lower than the height of that storage of water. So we've got here a reservoir, like right, so like a reservoir where you would hold drinking water for a town. So something like a lake or a pond that has an outflow pipe somewhere below the height, the top of that channel, that water, right? So, and this would work honestly for anything that has a small output from a large storage of water. So this could work for a water bottle or for a large storage vat of water, or a scuba tank full of air. So anything that has a large storage of water where the volume is relatively large compared to the small hole, this works really well. All right, so let's see how this plays out. So we're gonna have pressure at both openings, and they're both the same, right? So we have outside external pressure up here at the top of the fluid, and then our water is pouring out through the hole, and it's also going into atmospheric pressure up here, right? So P1 equals PATM, and then it's going out. The outflow is also into atmospheric pressure, right? So those two things are equal. So we can just get rid of those in our equation, and then we can simplify it to something that looks like this. Right, so we get rid of our pressures, and then we notice that once our pressures are gone, there's density in every single term here. So we could divide out density, and we're left with just our velocities and our heights times some other factors, right? And if we get our if we get velocity over at 2, or velocity of the water coming out of the hole over by itself, then we have 1/2 v1 squared plus gy1 minus gy2 equals 1/2 v2 squared. And you probably could see what we're going to do with our y's, which is the difference in height there is really just h, right? So we take our velocity, and if we multiply by 2 to get rid of those halves, then our velocity coming out of the hole squared equals velocity 1, or the velocity of this motion of water over here, so how quickly it's descending, squared, plus 2 times times g, the acceleration due to gravity, times the height, the difference in height between the top of that reservoir and where the hole is. If we think about those two velocities, our velocity coming out of the hole is going to be very fast, but the velocity that the large volume of water descends at is going to be very, very slow, very slow, right? So our V1 is going to be significantly smaller than V2 coming out of that hole. So it's so much smaller that we can approximate V1 as about 0, which means this term can just go away. And that leaves us with V2 squared equals 2GH, or V2 equals the square root of 2 times G times H, which might look very familiar because this specific simplified version of Torricelli's theorem, in which both ends are open to the same external pressure and the area of the container is significantly larger than the output opening, so that the velocity of the top is much smaller than the velocity at the bottom, at the base. You'll notice that if these conditions are met, then the size of the opening doesn't matter, right? So we don't actually care about the size of the opening up here because it's just so large relative to this small opening over here. And it's essentially just the speed of the particles if they had free fallen from that height, right? So back in our kinematics, if we solve our kinematics equation for V2 equals the square root of 2 times g times h if our initial velocity is 0. So that's kind of cool. Really, the speed of the particles coming out of this hole is the exact same speed as they would have if they were just in free fall from this height up here down to that vertical position. So we can play around with this, and let's say you poke a hole in a water bottle that is 5 centimeters below the open top. So we have to have this top open. But if we do, and if we got a hole here, then we can figure out what velocity we've got down through that hole, right? So we can derive the equation that relates velocity to the height, velocity at the hole to the height of the top of the water at the hole, and the or sorry. So we can derive an equation that relates the velocity coming out of the hole to the height of the top of the water relative to the hole. And that's basically what we just did, right? But you might want to take a moment to practice that yourself so that you can derive this on your own and understand why we simplified everything down to this. And then finally, you can also determine the velocity of the water output from the hole. I'm going to leave you to do that yourself because once we have the equation, it's very simple to plug in information. But something that's important to note is that literally all we need to know is the height, the difference from the top of the water to the hole, and then you can find your velocity of that water coming out of the hole. And we're going to practice that in class today when we work on all of this. So we will have plenty more problems to take a look at in class and to practice, and we will discuss this when we meet. Thanks for learning today.